Hey everyone, my name is Omar, and I'm going to be talking about understanding GPUs for game development. So a little about me to start with. I'm currently a graphics engineer working on the map at Snapchat. I'm living in Ithaca, New York, upstate New York here. I grew up in Alexandria, Egypt. And I used to make Flash games, back in the day, back around on Newgrounds, around 2009. Made about like a dozen Flash games, and I made one desktop game called Move or Die. And you can read more about me and see my work on my website there. So what I want to talk about, or like the goals of this talk are, I want to give you just like a basic understanding of how modern GPU hardware works, because that's how almost everything is rendered and drawn on modern screens and video games, but also in everywhere. And the idea is that by having this basic understanding, it'll help you just make better decisions when you're working on your game or in your engine. Like things like knowing when to optimize, like when something seems like you should be able to get a lot more performance, or when you should know that okay, I've actually hit the limit of what I can do here, and maybe I should redesign this level to have less assets, or to kind of have some kind of fake trick, like maybe put some more walls to make the levels a little smaller or something. It'll also, I think, help you recognize when, like, there's a lot of new technologies that come out, and oftentimes there's a lot of hype around, like, oh, well, this is going to make everything faster, much more performance, etc. And oftentimes that's true, but it may not be true in all cases. Like maybe something like, like an easy way to think about this is like, C++, the languages like C++ are faster than maybe other languages like Python or whatever. But just because you rewrite your game in C++ doesn't mean it'll be the game will run better, because it depends on why your game was slow. If your game was slow because you were just rendering a lot of things, or because you're loading a lot of data, or because of network, like if it's a multiplayer game, like it doesn't really matter what the language it's written in is. So understanding like these basics, I think, will help you just kind of situate where these new technologies lie. And finally, like just when I think when you know a little bit about how technology works and how the hardware works, it'll help you just figure out, like, know what's possible, and then you'll be able to do things that maybe haven't really been done before, or haven't been really explored, because the typical thing is most people just explore like what the engine gives them, what the engine exposes to them. But if you know what the computer can do and what the hardware can do, you could do something a little more custom, to understand kind of the boundaries of what is possible is. And then we'll look at some games, I think. Yeah, that's the outline. So I'm gonna just give you just an overview of the rendering pipeline, which is going to be, regardless of what engine you're using, this is going to be how things are drawn to the screen. So this should be generally useful knowledge. That's a fundamental thing. And then we'll look at some examples of games that have done this kind of creative use of GPUs by using this knowledge. And yeah, and then I'll just have a final example of like, okay, now that you know some of these basics, how do you apply this in kind of a real world example? Cool. Okay, so let's look at the rendering pipeline. And what I want to explain here is basically like how any modern computer, whether it's an actual desktop computer or a phone, or really any device with a screen today, how it puts pixels on the screen. So basically everything today is hardware accelerated. That's what a GPU is. It's a hardware accelerator for graphics. And I think a really good explanation of this, visual explanation, was this video Mythbusters did a while ago.
All right, I introduced to you Leonardo.
Where they show you, they have these like two robots, and one of them is like gonna draw something to the screen the way a CPU would. All right, so this guy comes in here. Yeah, so here's how you draw things on a CPU. You color each pixel individually. And this is how most of us are used to programming. If you think of the screen as just a piece of memory or an array, and if you want to draw a picture, you have to just color every single pixel. So you make a big for loop. You go over all of the pixels and you color them, and you do the instructions one by one. And so the more pixels, the bigger the screen is, the longer it's going to take, right? Because you're going to have to do more work, more instructions. Now, on the opposite side, here's what a GPU in this model would look like. It would be this giant cannon.
This trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs.
So basically, they're just going to fire this whole thing. And you can watch it. I think we're going to do a countdown.
When it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In 10,
9,
8, 7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over. Thank you.
So that's the idea. You kind of have this massively parallel thing, and it's going to draw things much faster, obviously, because instead of having to do each pixel one by one, you can do everything all at once like this. So these are kind of the two reasons why it's faster. Because it's highly parallel, so you can color all these pixels at the same time, but also because it's in the hardware. So, and I don't know enough about like the like whoever in the audience may be more familiar with electrical engineering can probably explain better why building a circuit that does something is always faster than writing something in software, because it's, you know, I guess it's more overhead built on a circuit. But those are the two reasons. The important thing is to understand why the GPU is faster, and it's because it does things are parallel, and because a lot of actual work instructions are not something that's written in software. It's actually something like in the electrical, in the circuit, in the way the circuit's designed. It's made for these functions, so it's going to be much faster than the equivalent piece of software that you could write. The other important thing to understand about the hardware there is that the GPU is a separate chip from the CPU, and that means there's some physical distance between them, and that means whenever you're sending things back and forth between the CPU and GPU, it's going to be slow. And this is a really important point that I wanted to just kind of go over a bit more, because if you get nothing else from this talk, really, the fact that CPU to GPU communication is slow and something that should be minimized is, I think, a really good takeaway. So let's take a look at an example here. Let's say you were trying to draw 1,000 circles on the screen. This is one way you could draw it. You have this loop over 1,000 circles, and for each one, each circle has an individual color and the individual geometry. Maybe the geometry is just the position on the screen and the radius. And in red is every time the red calls are here representing like sending data to the GPU. So what I'm doing here is 1,000 times per frame. I'm sending for each circle the color, and I'm drawing. This is going to be extremely slow, generally speaking, compared to how much faster it could be, because each time I do this, I have to wait for the data to go from the CPU to the GPU, and then once it's on the GPU, I'm only drawing. Like imagine this. Imagine you take this giant cannon, but instead of drawing the whole screen with it, you fire the whole cannon just to color like the top right corner, or essentially one circle. And then you load it up again and you fire the cannon all at once again, just to color another piece of the screen. And you keep firing this cannon 1,000 times here. It's going to be extremely slow, right? Ideally what we want is to just figure out a way to have it so that we can fire the cannon once and it colors the whole thing, draws all of our circles. So here's kind of another way where you could rewrite this to make it maybe 1,000 times faster. Here, I'm doing a bit more work on the CPU to gather all of the data I need ahead of time. And then, again, in red, I'm going to try and put all of the colors together for all of the circles, and then put all of the geometry together for all of the circles, and then I'll do one draw call, fire the cannon once. And one thing that's kind of missing here that's implicit is there's got to be some kind of index that ties these two arrays together. So the GPU has to know, and this is something we'll talk about maybe a little later, that, you know, the first piece of geometry, that's XY, and that should take the color that's RGB from that first array, and then you have to have something that can sync these two things across. But the idea is you just send all the data once, and that could be a little bit slow, and then you're drawing, and then that's extremely fast now that all the data is on the GPU. And yeah, when I say slow, these things are a bit relative, because you can send. My rule of thumb typically is think of it as like, yeah, you can send data from the CPU to GPU every frame. Let's say like, the character's moving, like things are changing. That's something that can be changed every frame. But it's not something you want to do a lot every frame. So like in this example, like the circles may be moving every frame. They may all have different colors every frame or different positions. That's fine. But I wouldn't want to keep sending for every single circle, send it to the GPU, because that will be very slow, especially as you get a lot of circles. And it's not that the GPU can't draw these things. It's that we're just waiting. We're waiting in between like the wires or that connect the CPU and the GPU. Yeah, and this is why a common thing is in a lot of 2D games, you'll have the sprite atlas. Because one thing you could do with that is instead of, let's say you have a character and then you have a bunch of ground, so instead of sending the texture to the GPU and then drawing and then doing that for every single object in the screen, you could just send this one piece of data, which is the image that has everything in it, and then you can draw everything at the same time. So you would send the image and also the positions of all the sprites you want to draw. And that way you can, again, do this in one big firing cannon shot. Similarly, in 3D games, this is why most engines will support instancing. It's often a little limited because if you're drawing like a 3D model that's instanced multiple times, there's some restrictions on how these instances and how different they can be from each other. But if you have a lot of objects that can be instanced, that is going to be much faster because, again, for a similar reason where you send the data once and you can draw many, many times. And this is a good example I found just from Googling on Reddit and Unity. This scene it's like this big scene with a bunch of grass and a lot of crowds in the background. And normally this could be like having to draw a lot of objects, but because it's using instancing, so all of the grass may be just one cannon shot, if you think of it this way. And when I say cannon shot here, thinking of the big cannon, this is like a draw call, is the name for it. So, and a draw call means you're asking the GPU to draw, and so that's gonna have to wait for the GPU to finish and then come back to the CPU and say I'm done. Then you can do your next draw call. So that's why combining them or making fewer of them is better. So in this case, this whole scene may be one draw call for all the grass, one draw call for all of the robots in the crowd in the background, and then we don't know how the trees is made, so it could be one object or one draw call on its own, or it could be multiple ones. Okay, so now let's actually look at the rendering pipeline and how that works, like the actual hardware. So this is a screenshot from this Vulkan tutorial about what is actually happening in the GPU when you're drawing things. And I'm going to ignore the tessellation and geometry shader steps because they're typically not available on a lot of platforms or in a lot of engines. It's a niche. I think it's a more niche thing, and I haven't seen it a lot personally. So we're ignoring that. So the first thing we have is at the top here. So what is the input to the GPU? Well, it's a list of triangles. Regardless of whether you're drawing 3D or 2D, you're always giving it a list of triangles. If you're drawing a 2D thing, usually you have two triangles that make up a quad, rectangle. So you give it the list of triangles that are in 3D, and then the vertex shader step gives you back the 2D coordinates on the screen, right? So you have these triangles that are in a 3D space, and then they get projected into where on the screen are they going to be drawn. Once you have these triangles on the screen, these 2D positions, now this is the rasterization step, which is taking those triangles and then filling them in, figuring out, okay, well, here's a triangle, how many pixels do I need to fill in to actually draw it? And then you have the fragment shader step, where you can compute the color, which could be like, again, on a 2D game, this could be where it could be a solid color, or it could be something where you get the image from a texture, because it's like an animated sprite or something that's hand drawn. Or if it's a 3D model, this is where you would compute the lighting, right? So you would have maybe you have a few lights in the scene, and this material is like shiny, or it's a grass or something. So based on the lighting and the scene, this is where you would compute that final color for that specific pixel. Yeah, and the stuff in yellow is the programmable parts. That's where you can write your own programs in this pipeline to change the output of these steps. The other parts you cannot change. They're just baked into the hardware. The hardware will do them, like the rasterization. You have some parameters you can provide to change what they do, but typically you can't write programs for them. Yeah, and so just as a side note, you'll see this word a lot, shader. What is a shader? A shader is just a piece of code. It's just a program that runs on the GPU. That's all it is. The reason we use the word shader kind of historically because traditionally the very first, like this actually used to all be non-programmable. The whole thing just did all these calculations and you were done. And then they started, this was like in the 90s or something, making it possible to write your own program. And so the idea was you were writing a shading program, a program that would change how the material reflects lighting, specifically like in the fragment shader step. So that's kind of why. But these days, like a shader can be doing anything. It doesn't have to specifically be something about lighting. But that is the common case for 3D games. Okay, so just to make this a bit more concrete, this quick demo I have here, and yeah, these slides we'll send them out if people are interested. So this is something you can fork. So I have it open here. This is just a small JavaScript demo with Three.js, and I have a little 3D low poly 3D model I got from Sketchfab here. And what I have here is I have a custom shader. Okay, so this is rendering, and I have the vertex shader and I have the fragment shader. So as we mentioned before, the vertex shader takes in positions that are 3D, and then its job is to put it into a 2D position. Okay, so let's kind of test this out. So GL position, that's the output of this shader. The input of this shader is the position here. So just as kind of a test, if I take GL position and then I say add to it 1. Notice that's going to move the plane here to the right on the screen, which makes sense because this is the x position of what I'm seeing on the screen. So it'll move to the right. But if I do for the y, instead should move up or down. Yep, I can see it moves up. Now if we were to do the same thing with the position that is coming in, the input position, we should be able to move it not on screen but in the world in front of us. So here, as I do this, you can see it's moving not quite right and not quite down, but just kind of like diagonally towards the corner here because it's moving like that way. If I do this again, it's probably disappearing because it's moving over there. And same thing with the Z. I think it'll move like up. I don't see it. Yeah, it's up there. Now here's the fun part. We don't have to stick to just moving or translating these things. We can put each vertex in a completely different position if we want to. And this is sort of what this commented out code I have here is going to do. What I'm going to do is I'm going to offset the Z position. Actually, maybe I can break this down. So what I'm going to do is I'm going to offset the Z position maybe by the X position. So that maybe is a bit confusing, but maybe that all that's saying is like for each vertex of this geometry, I'm going to move the Z position down by an amount that changes, and the amount that changes is the X position. So if something is at 0, 0, the first X near the origin, that's not going to move. But then as you go further along the x-axis, it's going to move. It's going to move a lot more. I could replace this with y, and instead of the ship being distorted along its wings, that's going to be distorted like front to back, I think. If that's the y-axis. Yeah. So now like the back of it is high up, and the front of it is down. And then I can do this fun thing with time where I can move it, across the wingspan, across the x-axis over time, and then taking the sine to kind of make that repeat. that's a very easy thing I'm doing on the GPU, and this is possible in any engine or in anything that is drawing any 3D geometry to the screen. This step always happens. This doesn't actually make it any more computationally intensive or anything, because the GPU is already taking in all these positions. It's already computing where they should be on screen. So adding just a little bit of extra change, that's a very easy thing to do. But the important thing is, remember that this is only going to change how it's visually drawn. This isn't changing anything about the 3D model, how the 3D model behaves. Like if this 3D model had like a collision around it, it's not going to make, the collision won't update, because the collision is a separate thing on the CPU side. You would need to go back somehow and update the collision for that. Let's go this back. Yeah, and real quick, the fragment shader is a similar thing. The goal of the fragment shader is to color the model. So the GL position here is the output. GL frag color is the output for the frag shader. So if I say, just give it this solid color, it'll be just white. I can make the whole thing red. The whole thing is red. I can actually visualize. So what this line is doing is it's saying, take the image. Someone drew an image. That's the texture applied to the plane, and this shader is saying map that image to the 3D geometry, and it maps it using this VUV variable. And one thing that's hard about GPUs is, again, because of this lack of communication between CPU and GPU, I can't just like print the value of a variable. That's not something you can really do. But you can paint things on the screen. So a good way to debug things is to just, if you want to know the value of a variable, just put it into a color and then look at it. So I'm putting the X into the red channel, and then we can look at it here. So what is this saying here? This is saying that the tip of this ship towards the front of it is black. That means the X is 0. And towards the back here, it's red. That means the X is 1. And it goes in between these. And I can do a similar thing for the Y. Alright, so I can see the Y starts out as 0 in both the ends of the wings, and towards the center it becomes 1. And so these values help you figure out, you can think of them, these are 2D coordinates. So for each point on the ship, it has to figure out which pixel from the image texture it should apply. And so that's what that is. And so when we put it back to applying the texture, actually we could do cool things, like if you wanted to move these, like imagine if I did this, if I applied a translation to this, it's going to slide the texture across. Let's see if I think I need to create a new variable here. So vec2 uv equal uv. Then I can move this one, and then I can move that one. So let's see, let's try to move it like 0.1. I'm not seeing any change. This one I didn't actually try before with stock. Let's see. Actually, I think you can maybe see a little bit. We can try to move it over time and just kind of see what happens here. Oh yeah, you can definitely tell there's, yeah, and because we're only moving the X, it looks pretty funky. So you can move the Y as well. Yeah. So now you get this kind of crazy effect. And again, this isn't actually that computationally expensive or anything. It's not going to make the game that much slower, because we're just kind of, we're not doing that much extra work. The GPU already takes the image and paints every single pixel. We're just kind of moving it slightly to kind of create this kind of crazy cool effect. Alright, so you could play around with this. There's a link to this in the slides. And that's, yeah, just to kind of summarize, this is this is kind of an overview of what is happening when anything is being rendered to the screen. You start with the CPU preparing a list of triangles that you want to render. And you have these two programs, the vertex program and the pixel program. If you didn't write them, then there's a default one that's being used, or the engine created one for you, generated from whatever settings or materials you have. But you always have these things, and usually you can customize them if you want. And as we saw, there's also some extra data you can put in with the triangles, like the UV stuff that tells you uh, for each triangle vertex, which part in the image does that correspond to. So that's what the UVs help you map to, as well as the actual image. That's extra data you can pass to the shaders. Yeah, and then the triangles go from 3D space to 2D space. They get rasterized, and then the 2D points are filled in, and that's again where you can write in your own code. And you'll see this word fragment shader, fragment program. You can kind of think of this as interchangeable with pixel program. So the vertex shader, its goal is to transform vertices. The pixel program or the fragment program, its goal is to paint the pixels. All right, let's take a look at some quick examples of games that I think do a good job applying some of this knowledge. One of them is Closure, and this is a pretty old game. This was popular in the Flash game days, but I like it a lot because it did something that I think no other games had done at the time. Basically, it's like this puzzle game where what you don't see doesn't exist, something like that. So you can see here, if you have a wall, right here. So here the character, let's say the character wants to go to jump down through the floor. They can't because the floor is solid. But if they jump and they're holding the light, then they can't see the floor anymore. And then what's going to happen is this box, because this floor is no longer visible, suddenly this box can now fall through the floor just because it's not visible. So it's a pretty cool effect. And it's something that's very easy to do with shaders, but shaders were not very common at that time, like a programmable shader, writing your own fragment shader. I wanted to just kind of think for a second, how would we design something like this? And so using what we were just kind of looking at, we can think of it this way. So you're already drawing every pixel of the ground. That's already something the fragment shader is doing. So what if inside that fragment shader you just say, before you draw this pixel, here's a list of light sources that you pass from the CPU. So just check, is this pixel close enough to the light source? If it's too far, just don't draw it, or draw it with like an alpha opacity based on how far it is. And that's it. It's basically like this one line of code if you can just send this light. And what that will do is you'll get this cool effect where you have, okay, here's light sources, and the light sources could be moving every frame. You just update the CPU, GPU once with the new positions of all the light sources. And you'll see that effect where parts of the level are going to disappear. The hard part then is, okay, but I want my character to be able to walk through it. That means you need to get the data that you just changed from the GPU back to the CPU, because you're not just rendering it. You want to actually make decisions based on it. You want the physics to update based on it. So there's a couple different ways to do this. If you're actually doing all this on the GPU, you could, instead of drawing directly to the screen, you could draw to an off-screen buffer, which just means you can draw it in such a way that you can get the pixels back, and then you could extract that data, then create like a new collision thing for that. The other way you could do this is to do the collision part just separately on the CPU. So on the CPU, you would have your own function to look for where the light source is this piece of collision close enough to the light source, and if so, disable it. There wouldn't be any communication between CPU and GPU, but maybe you wouldn't need to, and then everything would be fast because they'd be doing these things separately. Another cool example is Claybook, which has a pretty innovative rendering engine. Basically, it's this game where you can kind of mold and shape and create anything. I can watch it a little bit here. Yeah, so the whole world is kind of deformable like that, which I think is pretty unique. I haven't seen a lot of games like this. And there's a pretty cool talk they have here of how they did this. And a lot of it involves using the GPU to do computations that normally you might do on the CPU, but if you think of the GPU, because the GPU doesn't just do graphics, you can essentially run any computation and then extract the results from it. And then you can do these really creative things that impact not just the visuals, but also the collision and the world itself. There's also a similar kind of thing about Media Molecule's game Dreams, which also has, in order to allow players to like do all these really creative things, they essentially had to invent their own render pipeline. That's very different from what we were talking about, but still using the same hardware. So that's part of why, again, understanding how the hardware works helps you figure out that, okay, well, this is the actual input and output. I don't have to think about this as like triangles on the screen. I could think of this as like, you know, points in the simulation, or whatever you want to think of it as. And actually, an interesting example is Doom itself. Doom was made before GPUs were a thing, before any hardware acceleration. So there's a famous book, the Doom, I think it's called the Doom Engine Black Book or something. I have it linked there. Basically, it goes deep into how they made everything, including the rendering engine. And you'll notice the rendering engine, it's all the tricks they had to do is very different from what we do today, because they didn't have GPUs. So on one hand, you may not, it's interesting to learn for sure, but what you learn in that book wouldn't be very applicable to modern day hardware. But on the other hand, I think seeing how they made a lot of creative choices in how they're building the rendering, and how the rendering, I guess, influenced how the game was made, I think is itself it was interesting for me to see. And like one example is here, they show you how you know, one big problem was if you have a lot of rooms that have a lot of walls, that means you could be like standing in front of this big red wall, and that this red wall could have a lot of other walls behind it. So if you're spending a lot of time rendering those walls behind it that are never visible, well, your game is going to be really slow. So they're trying to come up with this like clever algorithm to figure out only draw the pieces of the walls that you can see. And in modern hardware, this is already done automatically for you. This is using a depth buffer. But understanding also that the depth buffer exists and what you can do with it, I think opens up other cool new techniques. Okay, final thing. This is kind of the final practical example I wanted to share here. So this is kind of a fun story. This is, I think it was about, 2021, so I guess 2 years ago now. There was kind of a little bit of drama where Casey Meritori, who's a famous game developer, was complaining on the Windows terminal GitHub that the terminal is very slow at just drawing text, colored text specifically. And at some point he kind of gets depressed here, and he's like, he tells them, you guys should be faster, and they push back, and they're like, making this faster would require like a PhD level project that is extremely difficult. And he's like, this is ridiculous. What's going on? And so I think this is a fun example because it's a good example of how a lot of people kind of think of GPUs as kind of this a little bit of magical black magic thing that they don't really want to touch because it seems a little intimidating or hard. But I think you don't actually have to be an expert for it to start being useful, even understanding a little bit of how it works. So there's a lot of details here. Like I linked to the full GitHub thread, and I think there's like a 2-hour video where Casey's talking about all the work here. But there's just one piece I think here that we can use the knowledge we learned today to kind of understand and maybe do better at if you were writing your own program doing this. So here's kind of the premise. Like the initial bug report was like when you render color text, it was rendering much slower in the terminal than if you were rendering all white text. Is that something that is normal? Like if you were building a program that had that, and would that just be okay? And in any case, is that something you can make faster, or is it just not possible? And the answer is yes. But the question is how do you make it faster? And this is the answer, but I'll kind of explain this in terms of what we just did today. So basically, what the terminal was doing is you have a lot of different characters. Okay, if they're all in the same color, they could draw them all together with one draw call. Again, fire the cannon once and it's great. But if they had different characters, well, now you couldn't do that because you needed to send that data with the character to the GPU of what color to draw. So what they were doing is they had this clever algorithm to like try to group together all the characters with the same color and then draw each group together. But if you had a lot of different groups, if the characters kept changing colors, it got really, really slow. But what Casey was saying here, he was saying, look, the fact that the text is monospace means you can do this clever thing. Like that each character can only be a certain size. So what you do is you break the whole screen. This is what's on the right here now. You break the whole screen into cells. And on the CPU side, you just say, okay, I'm going to draw, figure out what character needs to be drawn in every cell. And then for each cell also you have the character, then you have the foreground color, so that's the color of the actual character, and then the background color if the background color changes. And then that's it. And then you send all that to the GPU. So what you're actually sending is this. There's an index. This is a little hard to explain without being able to see both these textures that he's talking about. But what essentially think of it as one image is like the atlas we had that had Super Mario in it. One texture just has all of the characters that you want to draw, and then the other one is a data texture. It's a texture that just has a color, but the color doesn't represent anything. It doesn't represent anything visual. It represents which character to draw. So the important takeaway here is that this is what's on the right is a lot more work on the CPU, like a lot more instructions, a lot more actual things happening, but it's like 1,000 times faster, and that's because you avoid having to go back and forth to the CPU GPU so many times for every distinct group of colored characters. So even though it's a lot more work on the CPU, it doesn't matter because that's offset by how much faster it is once you do it all once per frame, and then you can draw everything once it's on the GPU, and then you're done. So I think that's a good example of just understanding, like, okay, like these very fundamental basics. Like I said, even just the idea that CPU and GPU communication is slow, and how do we avoid that, and that if you avoid that, things can be much faster. It helps you see what's possible. So that's it. Thanks for coming. You can find out more about me or reach out on my website here or on Twitter. I heard a saying about graphics programming that if it looks right, then it's right. But how do you actually approach debugging graphics programming? ده سؤال حلو قوي لأن debugging الجرافيكس programming بالذات shaders من أصعب الحاجات اللي بتخليها يونيك غير أي حاجة تانية. أنت في أي حتة ثانية معظم الوقت بتعمل إيه؟ بتبرنت الفاليو بتاع الفاريبل اللي عايز تعرف هل ده غلط ولا لأ، أو بتحط ديباجر. دول المين ويز انت بتديبج اي حاجه في العادي في الجرافيكس بروجرامينج في الشيدرز. You don't have either of those things. فبتعمل ايه؟ مفيش there's really no good answer صراحه. كل واحد عنده طرق مختلفه في معظم الوقت بتعمل ايه. زي ما انا كنت في التوك وريتكم، كنت وانا بكود كنت عايز اشوف مثلا اليو في فاريبل ده جوه ايه، فازاي بتشوفه. ما ينفعش تبرنت حاجة بس ممكن ترندر على الشاشة الفاليو بتاعه. فلو مثلا شفت لون أحمر يبقى كده الفاليو 1، لو شفت لون أسود يبقى كده 0. ف it's very coarse يعني. فبس يعني that's kind of it. مش it's not the best answer بس that's why مثلا معظم السوفت وير انجينيرنج بيبقى عندك unit tests وintegration tests وحاجات كده automatically ممكن تشيك الحاجات دي. that's why لكن في الجيم اندستري بالذات في الجيم بلاي تايب اوف ثينجز ما عندناش الفانكشناليتي دي، ما عندناش الانفراستراكشر اللي احنا ممكن easily unit test حاجات كتير. The best thing I've seen ان انت ممكن تعمل visually differing tests. فانت عندك مثلا scene بترندر وبعد كده تكوبي الاوتبوت وتشوف لو اتغير، بس برضه لو غيرت حاجه صغيره زي اللايتنج او كده بيبقى fuzzy test يعني. ف it's still not very accurate. But that's my answer there. There's another question about how does one go about properly learning shaders. the asker بيقول معظم الوقت لما تشوف shader tutorials on YouTube بيحط لك just a piece of mathematics وكود ولا copy paste وخلاص. Yeah, I think taking a step back and building things from scratch is the best way to do it. يعني مثلا لو بتشوف في ويب سايت اسمه شيدر توي، ده في ناس كتير بيعملوا شيدرز شكلها حلو قوي بيشيرت وممكن تأدت شيدرز مع بعض. في حاجات كتير شكلها جامد قوي، مش عارف في مثلا فاير افكت وسموك وحاجات كده. لما بتشوفها بتلاقي كود كتير ومش باين كل حاجه بتعمل ايه. فحاجه انا عملتها تاخد افكت زي ده بقعد اديليت جزء من الكود واشوف إيه اللي ناقص. عشان انت عايز تعمل العكس. لو واحد بيبني حاجه زي كده بيبدا هو بتعمل كل حاجه بتبدا تقريبا بساين ويفز. تعمل ساين ويف ماشي، بعد كده بتحط عليه ساين ويف تاني بيعمل شكل مور كومبليكيتد، بعد كده تقعد تحط افكتس على بعض على بعض. فهتلاقي الناس اللي هي بيعرفوا يبيلد حاجات كومبليكيتد كده بيبقوا فاهمين البيلدينج بلوكس. فدي حاجة بدور عليها دايما لما الاقي شيدر معقد وعايز اعرف بيشتغل ازاي. بقعد اشيل منه حاجات لغاية ما الاقي دي حاجة ووتر سيميليشن شكلها جميل قوي، بس في الحقيقة هي عبارة عن شوية ساين ويفز شيفتد ومالتبلايد وشيفتد ومالتبلايد. بس ودي حاجة اتعلمتها برضه لما شفت يوتيوب فيديوز بتاعت انريكو، ثانية اسمه ايه، اللي هو اي كيو، اللي هو الراجل اللي عمل شركته هو نفسه. هو عنده لايف ستريمز بيوريك هو بيبدأ ازاي ويكومباين الحاجات دي ازاي. أم، وفي برضه جزء تاني ان انت لو take a step back و learning not just about shaders لوحدها، بس الجرافيكس بايب كله زي ما انا كنت بحاول اعبر في التوك. في كتاب I'll post it بعد ال QA في الشانل. بياخد البايب لاين من اوله لاخره، وده كان احسن كتاب شفته. حسيت ان هو انا كده فاهم الداتا بتيجي منين وتخش ازاي، والفاندمنتال بيلدينج بلوكس دي بتخليك تبني حاجات اسهل. تالت سؤال هنا: Is using visual shader tools like in Unreal Engine and Unity sufficient for most development needs, or does writing shader code provide more API features that are otherwise unreachable? Um, it's a good question. I think عندك في Unreal Engine و Unity بيبقى في either like a blueprint or visual editing or just making material nodes. معظم الوقت دي كفاية، وبالعكس انت ممكن الحاجات دي تخليك تعمل حاجات احسن من انت ممكن تعملها وانت مجرد بتكتب شيدرز. لان انت عشان تكتب شيدر بيعمل complex lighting وحاجة كده هي صعبة. يعني ما حد يعني nobody بيقعد مجرد ان هو يكتب شيدر كود. يعني عارف معظم الناس اللي شفتهم الجرافيكس انجينيرز بيبدأ الأول بالورقة وقلم أو حتى في بلندر، بيفكر هي اللايت جاي منين ولا إيه الإفكت اللي أنا عايز أوصل لها، بعد كده بيحاول يكتب الكود. ف في most things I think these tools are fine. الحاجات اللي ممكن تبقى محتاجها شيدر كود لو بتعمل حاجة آم، غريبة ما اتعملتش قبل كده، مش ستاندرد، زي ما كنت بوري مثلا كلوجر اللي هي الجيم اللي لو حاجة لو في اوبجكت مش موجود في اللايت الاوبجكت ده بيختفي او بيبقى مش بيبقى في الكوليجن نفسه. um, او زي حاجه زي كلاي بوك والحاجات اللي هي مش موجوده اصلا في الانجنز. um, واتس also fun. يعني هي حتى لو انت عمرك ما هتكتب شير كود I think just understanding ايه اللي ممكن يتعمل. لان انت مثلا واقف في الماتيريال اديتور عندك 7 اوبشنز، بس واحده من الاوبشنز دي هيبقى بطيء، واحد من الاوبشنز ده ممكن تعمله مش هيبطئ الجيم. وعشان تفهم الفرق بينهم يعني بيساعد ان انت تبقى فاهم انت بعد ما تغير الاوبشنز دي ايه الشير كود اللي بيطلع اوتوماتيك. فانت مش محتاج تقعد تكتب شير كود اوتوماتيك، بس I think it helps ان انت تبقى فاهم الشير كود اللي ultimately الانجن محتاجة تطلعه يبقى شكله ايه. آخر سؤال، وI know احنا عندنا 1 minute left. Any resources you recommend for getting started on learning GPU shaders? Um, Yes, I'll post some resources. I think في tutorials أنا كاتبها، وفي كتاب um, اللي I mentioned earlier اللي هو نسيت اسمه، بس أنا هحطه في الشانل دلوقتي. بس I think that's it. شكرا للجميع for being here, for inviting me.
Thank you for coming وtalking digestible جدا. I really appreciate all your effort I hope يعني إنها كانت beneficial لناس كتيرة.
Thank you so much.